Francesco. I'm a game developer advocate. Really, I'm a game developer. I've been making games since 1999, give or take. I'm a graphics engineer, so I'm super excited to talk about Vulkan. It's graphics APIs. I'm a geek, and it's going to show. I worked on several engines in my gaming career. Who has ever played Fable 2 here? She did? Yep, that's my work. It's my engine with others. And I also work on CryEngine from Crytek, the does it run on Crysis thingy. So I'm a geek about graphics APIs. And today I'm super excited to share this stage with two titans of the Vulkan ecosystem. Here with me, Tom and Jungho. They will show you various tools and best practices to bring to life console quality experiences on mobile, which is unprecedented. We're going to talk about the Vulkan ecosystem, which is a big ecosystem, and Tom will go in great details about it. And then we're going to talk about tools, because, I mean, really, an ecosystem is as good as the tools that you can run on. If you remember back in the day, the Xbox 360 and the PS3 times, the PS3 had arguably better hardware, but the games on 360 were probably looking better for a long time because of the amazing tools that were running on the platform. I am super biased because I worked on the 360. But someone working on PS3 would tell you that their tools were amazing too. That's why they could make fantastic games. So we're going to explore tools on running on Vulkan. And now, what do you use a tool for? Well, use tools for improving game performance. And Jungho will show you how you can use these tools and you can use best practices to literally make games sing using Vulkan. And then we are not going to have Q&A. I don't know why it's there. But you can come afterwards. So let's come talk to me. Here's the thing. I am here standing on the shoulders of these titans to tell you that Vulkan is viable on Android. It's been a bumpy road. There are issues, we know, but I personally worked on games that either ship Vulkan only or shipped with Vulkan render that are making games. And they're making money. Vulkan is viable, and we're going to go to great lengths to show you how and why. One of the characteristics of Vulkan is, well, the driver overhead is much lower compared to OpenGL, which basically means that things like state validation that in OpenGL happens all the time. Like, you're submitting a draw call, and the driver's like, are the states correct? Yeah, they are. Submitting another draw call, but are they really correct? Yes, they are. You checked right a second ago. In Vulkan, it's something that you do once. You cache, you build your state pipeline, and off it goes. You render as many draw calls as you like with that pipeline, and it's immutable. It doesn't need to be verified every time. This means lower driver overhead, lower CPU consumption, lower CPU usage, and lower power consumption. CPU consumption, I mean, you can use CPU as much as you like. Which is, for me, one of the main reasons to start thinking about Vulkan. Your CPU will be engaged reasonably less than with a standard OpenGL render, which means that you're going to give more chances to the various cores to go to sleep and consume less power, which also means that you're going to have less chances to go into thermal throttling. I talked yesterday about it for about 20 minutes. Lower power consumptions means longer battery life, which means more money in your pockets. Also, Vulkan has been designed from the ground up from the beginning to be a multi-threaded API, which means that you can build your common buffers in parallel on several threads. You're not stuck anymore into this world where all your commands are serialized into one thread, and then off they go to the GPU. Now you can take full advantage of the multi-core architecture that we run our phones on. Again, multi-thread API means shorter render frame times, also means more chances for the various cores to go to sleep, less battery consumption again. And here is what I like the most about Vulkan. The fact that I'm a graphics engineer, I write this engine, I know when the shadow buffer happens, I know when the various render targets I'm rendering to need to be rendered to, I know which texture I'm using, I know everything about my engine. At least I hope so. I can tell the driver what resources depends on what resources. I don't need the driver to try to figure it out every frame from what I'm submitting. I'm in full control with Vulkan, and with control comes great responsibility. There is a higher chance to get it wrong. And Tom will show you how to detect these cases and do something about it. This is the latest CryEngine demo that was featuring ray tracing. It's a Vulkan demo. It looks stunning. And it runs on mobile. Without the ray tracing part, but this thing runs on mobile. It was running on my Pixel 3. This video is coming from my Pixel 3. It's a direct capture. They ported this in 2 or 3 weeks. Can you play it? Thanks. I strongly encourage you to come over there and see it running on device. This is unheard of. Special thanks to Murat and Vladimir, who put up this demo in no time. I was amazed at seeing it running. And now it's time for Tom. Thank you.
Thanks, Fran. So first, to correct all the things he said that are wrong. We're not going to go into deep detail about debugging tools or the ecosystem because we only have 20 minutes, and it's a big thing. And so what we're going to do is take a very high-level view of just a little bit of it, and then I'll go into great detail on a few things that I think are exciting. I'm kind of assuming that Vulkan is not new to most of you. You kind of know the basic principles. And at least some of you are probably more skilled than I am. Because, by the way, I should say, he's a game developer. I'm not, never have been. Sorry about that. As to who I am, my name's Tom. I work for ARM on the Mali GPU team, and I also chair the Vulkan Working Group. So I have 2 hats with me today. I'm going to talk from both perspectives. I will try to be clear about when I'm talking about what. So 10,000-foot view, I tried to draw a picture. And the conclusion was, it is complicated. I don't mean that in the creepy social media sense. I mean that there are a lot of moving parts. I work mostly in the red stuff over there with the specifications, conformance, validation, but there's a whole army of people working, including your friendly neighborhood dev techs, at least one of whom you'll recognize on the right. The point of this slide is not to say that it's complicated. It's to say that there's a lot of people, a lot of software teams working very hard across the ecosystem to make Vulkan a good platform. The whole ecosystem is much bigger than it looks from the outside. What this slide doesn't show is the growth that's been happening. I tried to draw a picture of that. It was a total non-starter. What I'll show instead is just a few quick slices through the data to give you some sense. So one thing I track is SDK downloads. I don't actually have the data for Android, I'm sorry to say, because their SDK is bundled. But for the Vulkan SDK for desktop, this is what we're seeing. It's noisy, but the growth is continuous. I also like to track what's happening in open source. Monday night, I went to GitHub and typed Vulkan at the very top level search box, told me there were 3,126 projects that mention Vulkan. I've been doing that for 3 years, and I can plot the data, and it's as clean as a whistle. It's either linear or the second derivative might be slightly positive, but the rate of growth there is very impressive as well. One of the things that my committee worries about most is making sure that you have quality drivers to develop on. So when we write specs, we also write conformance tests in as much detail as we can afford to make sure that implementations that say they implement the spec actually do. So we launched 3 years ago with 100,000 test cases in conformance. We're at 400,000 today, and you can do the math. Again, it's pretty linear. So we expect this to continue indefinitely. We know it's working because every time we add tests, the GPU vendors come back and say, oops, and then they go off and they have work to do. So that's a good thing from my point of view. Finally, of course, there is content. It was kind of a slow ramp in mobile, reflecting the fact that it took Vulkan a while to build up a substantial footprint in the market. Last year was the year when Vulkan really became a thing on desktop. This year, it's really a thing on Android. So a lot of very high quality stuff shipping. That's all the detail you get on the ecosystem as a whole. Sorry, that's all I have time for. What I would like to do is zoom in from 10,000 feet to 10 inches, talk about a very narrow advance in the tools ecosystem that I'm really excited about and looking forward to seeing people use. It's called GPU-assisted validation. Work was done by LunarG with funding from Valve and in consultation with the working group. They're both members, and we all go way back. I should say, all of this part of the talk is with my Vulkan hat on, talking for the working group, not for ARM. So hopefully you know how validation works. When your application calls a Vulkan entry point, it's going through an ICD table and reaching a hardware-specific, GPU-specific driver underneath. And that ICD is doing no error checking at all if it can help it. It assumes you're using the API correctly. If you're not, something will happen, but it's not the driver's problem. So that's one of the reasons, as Franz said, that the drivers are very efficient, very fast, but it's a hellish debugging environment. So to make debugging and development possible, we provide validation layers. So you can tell the loader, when it initializes the ICD interface, to insert validation underneath. Then when you call into those entry points, the validation layer checks them, tells you if you're doing something wrong before it passes the data to the ICD. This works great for things like invalidity num. It works for things like I'm passing in shader code, which I hope you know how SPIR-V works. If it declares a SPIR-V capability that your hardware doesn't support, it can catch that kind of error. Those are all static errors. Unfortunately, most of the interesting errors are dynamic. So for example, you might have a GLSL shader that starts out declaring an array of 6 texture samplers. And if in your code you reference one of those and you reference outside the array, that's a static error. SPIR-V validation will catch it, but actually the compiler, GLSlang, will catch it first, so you will fix it and you'll be fine. But if your code's doing something dynamic, if the index is coming from a shader stage input or a buffer or a texture, the compiler can't do anything and you're hosed. So what's going to happen if you actually execute this code and that index is out of range, the spec says you get undefined behavior. If you're lucky, what that means is it draws your geometry and there's a texture corrupt or missing, and you can look at the picture and figure it out. But honestly, you're usually not that lucky. Usually you either get device lost or you just get something totally weird and you just have no clue what's going on, and it takes you days and days and days to figure it out. So now we have something better. This is as of GDC. Again, we've made progress even since then. The way this works, your application wants to make a shader. It loads in a SPIR-V blob. That's the binary intermediate shading language. It passes it to create shader module. If you have this validation enabled, the shim, that is the validation layer implementation, grabs the blob, runs it through SPIR-V opt, which is a general purpose shader transformation engine. And that SPIR-V opt in this mode goes through, finds all the references to texture descriptor arrays, and sticks in extra SPIR-V code around them to check, is it in range or not? If it's not, write an error log message, and also coerce it to be legal so that hopefully you won't get device lost, at least not right away. So that gets passed back, goes down into the native driver, and the whole schmear gets compiled. When you eventually run a command buffer that does this, that contains this code, after the buffer completes, validation checks the log and sees if there's something there. If there is, it writes you a human-readable message. So it's a lot of text, but there's a lot of information here. So it tells you, for example, what's the name of the error. They're supposed to have error ID codes. Sorry, we didn't get around to that yet. It tells you the details. You indexed out of range exactly like this. It gives you the handle of the command buffer, which is okay, but mapping it to your code is kind of awkward. So fortunately, there's a debug extension called ext debug utils. You can use that to give symbolic names to your objects. And if you've done that, the log message will include a name, the symbolic name of the object, as well as the handle. Tells you which draw call, in this case the first one. Gives you pointers to other objects involved, the pipeline state object and the fragment shader. Tells you the invocation as best it can. So in the case of a fragment shader, it gives you the frag coord where this error occurred. Often you can look at the scene and see what was being drawn or infer things about it from that. Gives you the index of the SPIR-V instruction. In order to actually use that, you have to run the SPIR-V disassembler on your blob and read through it, jump to line 116, and see what was happening there. It's not the easiest thing in the world to figure out. Fortunately, as part of this project, we also added debug support, that is -G support to GLSlang, the shader compiler. So if you're in this situation and you debug -GS, this log message will include the file name where your error occurred, the line number, and it'll print out the source line, which is way cool. It's almost like debugging a real computer. A few things to note. There are version dependencies. There is a performance cost. It is going to perturb the time course behavior of your application. The two most important things, it needs a free descriptor binding slot. If you're working on an implementation that only has a few and you're using them all, it's not going to work. We have a fix for that in flight. It's not here yet. The other thing is that currently it only checks image and texture descriptor arrays, but that's just us driving the golden spike. Obviously, this is extensible to all kinds of things, and in fact, we've already landed partial support for the ext descriptor indexing extension, aka bindless. So if you were waiting for that, you know bindless is kind of nasty to debug. We have a fix for you coming. So more information available. Thanks again to LunarG. So, switching to my other hat. You all saw the hat, so I can take it off, right? Like most GPU vendors, we have a developer support team based in Cambridge, UK, but with outposts around the world. And their mission is to help you use Vulkan well, use it efficiently, particularly on Mali, but most of what helps on Mali helps everywhere. So making Vulkan great is part of their mission. And they do that typically first by one-to-one interactions with you. If you file a support issue at malideveloper.com, they're the guys who answer you and work with you. That doesn't scale well, so they also do blog posts, they do sample code, tutorials, etc. That scales, but it is hard to build intuition. You have to read it over and over and talk to people. It's kind of annoying. So in hopes of making that situation better, what we released at GDC this year is a toolkit we call the Vulkan Best Practices Toolkit. This bundles together tutorials, it's sample code that shows you things we think you should do, also shows you things we think you should not do. So we have that together with text tutorials that walk through it and explain the whys and wherefores. But then the thing that's new and I think novel is that there's also a plugin framework that all of these samples plug into so that you can experiment with them, toggle the recommended and non-recommended practices on and off, and see how that affects performance. So if you look at it, in this case, this is a sample that looks at load store ops at the beginning and end of what you do with a frame buffer at the beginning and end of a render pass. And it lets you just toggle between different options for the depth attachment and the color attachment. Important to note, the scene in the background is totally boring. Can we play that again? The scene in the background is boring, but that's configurable. All the source code is there. You can load different scenes. You can add your own. There's a GLTF importer. You can put your own objects in it. So you can try all sorts of things. You can change the shaders and see all sorts of things happen and experiment with it. Thanks. The other thing to note is that it's multi-platform. It is not Mali specific. Some of the performance counters that print out at the top are Mali specific, but you can run this code on an Arduino device, and you'll see what happens in the case of demos that have frame rate as their principal metric. You can see differences between how Mali reacts to something and how Arduino reacts to it. And that's by design. We want you to have that information. Other things to say about this. Also included in the project are guides to using our more advanced development tools, which I'll talk about in a minute. As I said, it's all on GitHub, it's all free, and we're working on trying to share this code base with other GPU vendors in the Android space so that we give you a better basis for exploring the performance quirks of different GPUs and tune your code. In other words, don't always take our advice. It might be bad on another GPU. You need to make that trade-off, and we want you to have the information to let you do that. So the last thing I'll talk about is what I call the power tools. These are the tools that our support team uses if you call in with a problem they can't figure out, and you send them code, and they have to sit down next to you and explore it. There's two. Graphics Analyzer is one. This used to be called Mali Graphics Debugger, and it used to be Mali specific. It no longer is. To be quite honest, it's very similar to RenderDoc. If you're using RenderDoc today and you like it, you may not need this. The only thing it has that RenderDoc doesn't is it's more aware of the performance counters that Mali exposes. We're hoping to add that capability to RenderDoc. So it's a good tool. We use it all the time, but it's not something that you necessarily should go and download unless you're working with Mali a lot and having trouble. The tool I do recommend that everybody check out is Streamline. This is the total ARM ecosystem performance analyzer, which gives you sort of systrace-like traces of what's happening on all the CPU cores, processes, etc. It also does that for all the GPU cores if it's Mali. And It also allows your code to inject events and put little flags into the code so you know exactly where to look. It's really quite awesome. There were two things about these two tools that used to really bother game developers and that kept a lot of people from using them, and they kept telling us we can't use it. Those things were, it cost money, and you had to root the phone you were running on in order to have access to the performance counters. So I'm very pleased to say, as of GDC-ish, there's now a starter edition which is free. So you can try it, kick the tires, see how you like it. And the other thing, with some caveats, you no longer have to root the device. That is assuming that the device is written according to our guidelines. We're working with our partners to get them to do that. Some are quick to do it, some are slower. If you have companies like Samsung that are very dedicated to providing a good developer experience, they are very quick to adopt, so S9 is supported. S10 will be supported in about 2 months. There are some things we have to fix on our side that are keeping it from working. We have a list online. You can go and see what's there. So there's links, which I hope you can find online. And with that, I'll turn it over to Jung Woo, my good buddy from Samsung. Sorry, Nan.
Thank you, Tom. Hi. I'm Jung Kim, reading GPU and game dev in Samsung Mobile. I will share the Vulkan optimization practices from our partner collaboration. Before jumping into that, I hope to give you some introduction first. The game is so important for Samsung because that what we really care is not just device, but also user experience comes from the device. The high-fidelity game is one of the most serious and hard to achieve user experience in mobile, because in mobile, everything is limited by form factor. The fundamental performance difference between PC and mobile comes from the difference of the thermal design, power budget, and battery capacity within this form factor limitation. And even we keep chasing the peak performance, peak is not something you can keep using for sustainable workload like gaming. Because of this, optimization is so important in mobile than any other area. Not for the trade-off optimization between quality and performance, but for the real optimization for great performance within even higher fidelity. The new technology to break through the fundamental problem are essential, like Vulkan 64-bit multi-thread rendering are those. We believe Vulkan is the most demanded new technology to achieve this, so we've heavily focused on Vulkan for recent 4 years. To accelerate the adoption of Vulkan, we realized that making many best practices with real market games are required. But game developers are always busy, so we announced the Galaxy Game Dev at 2016 Samsung's new game developer support program, helping Android game ecosystem with adoption of new technologies. These are our key partners, and you can see both big players and also the indie developers. You can see both the Unity and UE4 developers at the same time, the multiple in-house game engine developers too. They were taking the risk to bring new technology into their game development and always aiming higher goal and quality and performance. I want to say thank you to all partners to give us a great chance to work with them. The game dev team has around 30 game dev engineers from 5 different locations. They work hard, sometimes on site, the partner developer studio, sometimes also remote support at their offices. And also hope to say thank you to the team for your all contribution to show bright future of the Android gaming ecosystem. During the collaboration with the game developers, we learned a lot. There are 4 key areas of game optimization we think. About tool and SDK, Google and GPU vendor like are now work hard, as Francisco and Tom already mentioned. So now I focus more on the other areas: GPU driver, the game engine, and developer support. All these 3 are not perfect at this moment in Android. That's true. The first, GPU driver. The quality and performance both are two main requirements from Android game developers. We are co-working tightly with the GPU vendor like Arm for optimizing GPU driver. This is the graph of the GPU frame time of a heavy GPU seen in Fortnite. It took around 29 milliseconds in March, but now it reduced to the 22 milliseconds in November with the same multi-GPU. Average frame gain is around 5% just with the driver software optimization. Improving quality of a GPU driver takes a longer time, so for accelerating the progress of this, we are working with Google to enhance updatability of GPU driver in Android. This will bring better way of updating GPU driver by Play installation and hope to ship this feature as soon as possible to help both game developers and also end users. Even with better quality and performance of GPU driver, game engine is also one of the big areas to make Vulkan support well for the real game development. Unity and Samsung agreed to support early Vulkan Unity developers at 2017, and now multiple Unity games support Vulkan and show real performance benefit. Final Fantasy XV Pocket Edition is one of those. We had a 4-month on-site camp at Okinawa with Square Enix and Summertime Studio. We did many Vulkan optimization on Unity Bin-Train render, and finally we got the 42 to the 60 frame per second performance gain. One of the main optimization we made was about pipeline barriers. Let's talk more about the pipeline barriers. We picked up the heavy vertex job example to show impact of using wrong pipeline barrier set. This Vulkan sample is showing the serialized vertex and fragment job during GPU processing with DS5 streamline capture. So performance is not that good, the 62 millisecond GPU frame time. A pipeline barrier creates an execution dependency between the two active pipelines. Execution of the current random path will wait at the destination stage until the execution of the former random path has completed its source stage. And considering the narrow down to the two random passes, an example shadow and main, with the naive case, main always wait until completion of all pipeline stages in the shadow random path. All vertex, fragment job are not fully parallelized, and those two random passes take 28 milliseconds. If we consider pipeline barriers set more optimal in this case, we can set beginning of the fragment stage for the main random path just need to wait until the completion of the shadow random path. After changing pipeline barrier set, you can see shadow and main random paths are enoughly parallelized. And those two random passes take less time now, the 22 milliseconds. We can optimize all random passes of this sample with same manner and see overall frame time reduced from the 62 milliseconds to the 40 milliseconds. Same workload, but take less time. We also supported the Tencent TME Studio L1 for Honor of Kings. Vulkan helps a lot to improve the performance of Honor of King, and even with the S7, it showed a big performance gain, like the 41 to the 53 frame per second. Another optimization we made is offloading unnecessary road store operation. Each attachment of random path has a set operation for road and store. This should be carefully managed to avoid unnecessary overhead to road and store the attachment between the on-chip memory and host memory. 100 sold by HOUND 13 also gets a noticeable performance gain by Vulkan, and the random path road store optimization also helped a lot in this case too. You all know Samsung and Epic Games had a good relationship. We worked together developing Protesta demo and made the same agreement to support early Vulkan UE4 developers too. So we did many contributions to UE4 Vulkan. One of the recent UE4-based collaboration was the Tencent game for PUBG Mobile. And we did many works about update descriptor set. Let's talk about the descriptor set more. In GLES, the process of setting uniform data is simple and readable. But how about the Vulkan case? First, we define how many descriptor type is needed on the pipeline stage, and allocate a descriptor set with that information. After this, should prepare the information of a uniform buffer and image in the right descriptor set structure. And here we need to allocate a BK buffer for uniform data. Now we can update descriptor set with the calling BK update descriptor set and bind the descriptor set. Finally, we can use the data or image on the pipeline. It's so complicated, but let's forget about it. Please just remember we need to allocate buffer and call BK descriptor set. In ideal case, which has a static object and view direction, we can allocate the VK buffer once and update the set initially, and just reuse them everlasting. But in real cases, things are more dynamic. We cannot predict which object are generated or destroyed. And so whenever the objects are created or destroyed, we need to allocate or release the buffer every time. And this will cause a huge overhead in CPU. Solution is allocating a huge buffer and using offset on the buffer information structure. In this case, we can avoid the frequent allocation of the BK buffer. But because of buffer information structure is a part of the BK write descriptor set, so we still need to call BK update descriptor set every time before binding a descriptor set. Better solution for avoiding overhead of calling update descriptor set every time is using dynamic offset when binding descriptor set. In this case, dynamic offset when binding descriptor set, in this case, we can set the offset value on the buffer information as 0, and we just deliver the offset information with a dynamic offset array in the BK command bind descriptor set. With summary, this optimization is mostly CPU side off-roading. We could manage BK buffer by using offset. We also could manage BK update descriptor set calls by using dynamic offset. With the spoken sample, using offset case shows about 19 frames per second and still CPU bounded. Using dynamic offset case shows the 24 frames per second and now less CPU bounded, but more GPU working. Android systrace show the 25 millisecond taking a BK update descriptor set is gone after dynamic offset optimization. The off-roading CPU helps the GPU works better and more. Try is very recent work with Nexen Moai games, and update descriptor set optimization helps a lot too. And this gave a 35 to the 56 frame per second gain by overall Vulkan optimization we did. The Galaxy Game Dev support the game developers who want to develop high-fidelity Android games. We support to optimize partner games and GPU driver for better Vulkan support in Galaxy devices. But from this, all we found goes to the GPU vendor and the game engine companies for wide distribution. We are also contributing to the Android with Google and Vulkan working group within Khronos. Our final goal is improving overall Android gaming ecosystem better. Thank you.